The question was to write the first four terms of 1 plus 1 over x to the 1/2 power. And while you could try to do it using, well, you can't really do it using, I mean, the problem is you can't do this one just using the straight up Maclaurin series because you can't center it at 0 because 1 over 0 is undefined. So the issue here is that you'd have to really kind of, you can't do this one as is. Because it's actually not a Taylor polynomial, right? When we actually write it out, it's not going to be a polynomial. You're going to have powers of x that are not positive integers, which is okay. But the idea is you're going to use just the formula for binomial, what do they call it? Binomial Taylor polynomials, which is that 1 plus x to the mth power, where m is any real number, is equal to 1 plus the infinite sum from k equals 1 to infinity of m choose k, and we'll talk about how this is defined, times x to the k. M choose 1 is m choose 2 is m times m minus 1 over 2 factorial. And basically, m choose a number is m times m minus 1 times m minus 2 all the way down to m minus that number plus 1 over that number factorial. So here's what we're going to do. To figure out what 1 plus 1 over x to the 1/2 is, we're going to first just do 1 plus x to the 1/2. And then we're going to replace the x with 1 over x, just like one would, right? Just like if I was trying to find what sine of 1 over x was, I would write the polynomial for sine of x, and then I replace the x's with 1 over x's. So I suppose interestingly, before we do this problem, let me show you what e to the negative x, sorry, e to the 1 over x, if you wanted to write the, I feel like polynomial is not quite the right word for it. If I wanted to write the, sorry, one second, I'm trying to think of the right name here. Yeah, I guess it's just the series, right? If I want to write the binomial series for this, that's kind of, well, anyway, if I wanted to write the power series for this, how about that? I could write it as, I know that e to the x is 1, sorry, is equal to 1 plus x squared over 2 factorial, etc., etc., etc. So e to the 1 over x, just taking the x and replacing it with 1 over x, this would be 1 plus 1 over x plus 1 over x squared over 2 factorial, which you could totally write as 1 plus 1 over x plus 1 over x squared times 2 factorial plus 1 over x cubed times 3 factorial, which again, right, isn't positive integer powers of x, but that's okay. It's kind of weird. Some things are weird. Question, actually, I'm curious. Yeah. All right. So for this one, here's what we've got. So I'm just using the formula. And this is in the book, right? This is in section 10.10. The binomial formula is totally given. I've never memorized it, but it is there. So we have the 1 plus x to the 1/2 is 1, plus then the first term is 1/2 choose 1 times x to the 1, plus 1/2 choose 2 times x squared, plus 1/2 choose 3 times x cubed, plus more terms, but the question only asks for the first 4 terms. So then 1/2 choose 1 is just 1/2. 1/2 choose 2 is 1/2 times 1/2 minus 1. And 1/2 choose 3 is 1/2 times 1/2 minus 1 times 1/2 minus 2. I should, sorry, 1/2 choose 2 is 1/2 times 1/2 minus 1 divided by 2 factorial. 1/2 choose 3 is 1/2 times 1/2 minus 1 times 1/2 minus 2 divided by 3 factorial. So calculating the things, 1/2 times negative 1/2 divided by 2 is negative 1/8. And 1/2 times negative 1/2 times negative 3/2 divided by 6 is going to be 1/16. So the first 4 terms of 1 plus x to the positive 1/2 is 1 plus 1/2 x minus 1/8 x squared plus 1/16 x cubed. And now to figure out what 1 plus 1 over x to the 1/2 is, we're just taking each of these x's and replacing them with 1 over x's. So this is going to be 1 plus 1/2 times 1 over x minus 1/8 times 1 over x squared plus 1/16 times 1 over x cubed. So the first 4 terms would just be these first 4 terms. And you could, I guess you could write it slightly more simply. You could write it as 1 plus 1 over 2x minus 1 over 8x squared plus 1 over 16x cubed. And although they don't ask you for it, it is worth noting that this, if it's the infinite sum, converges for x between -1 and 1. So this, since it's 1 over x, it converges for 1 over x between -1 and 1, which means x has to be larger than 1 or less than -1. Kind of interesting. The binomial series is always a little bit strange. Yeah, I feel like I wish this said a little bit more about the fact that you are getting something that isn't actually polynomial looking because you have powers of x that are non-positive. But they do not. Okay. If there are other questions about Taylor, Maclaurin, power series stuff, feel free to send them in the chat or whatever. I'm going to go talk about some chapter 14 stuff. Excuse me. Chapter 14, 3D stuff. I mean, it's kind of a mix of 3D stuff and then talking about functions. So talking about like, mostly talking about like z as a function of x and y. So if you're thinking of z as a function of x and y, you're typically thinking of some surface being a function of x and y. Let me grab my notes here before I get too carried away. And really what we're working towards is talking about partial derivatives, where you're differentiating a function of multiple variables with respect to one of those variables. Before we get there, we have to kind of figure out what functions of multiple variables look like. So where did you go? Examples? Sure, okay. So let's look at some functions of multiple variables, like the following. F of x comma y equal to x squared plus y squared minus 4. We're going to do kind of everything we can with this, but a couple things we like to do with these functions. We like to think about the domain and the range. So in fact, let me just kind of list everything out. So we're going to talk about domain. We're going to talk about range. We're going to talk about level curves. I put curves in quotes there because, well, you'll see. And then I don't think the textbook actually mentions it, but we're also talking about the traces, because I feel like the traces are super useful if you're actually trying to graph the 3D surface. Domain, range, level curves, traces. Anything else I'm thinking about? Not really. Okay, so let's talk about all the things. So domain, the usual domain rules apply. Meaning, do we have any division by 0? No. Do we have any square roots? No. Do we have any logarithms? Also no. So if you don't have any of the usual domain function issues, actually function domain issues, the domain is going to be everything. I should also say, I guess a couple other issues you could have would be inverse trig functions, but usually those don't show up. So here the domain is everything. Now I should point out, this is going to be slightly different than the domain was for your regular functions of one variable. So if your function was something like, you know, f of x equal to x squared plus 3, the domain is everything, meaning the domain is all real numbers. You can either say it's R, or you could say it's the set from negative infinity to infinity. Here, the domain isn't just all real numbers, it's all coordinate pairs. Right? It's all possible combinations of x and y. So here the domain, you could write it like in 3 different ways. You could write it as the set containing all points x and y, such that x and y are real numbers. Or you could write it as R2. You do say R2, not R squared. Some people say r squared, but r2 is the more usual way of saying it, which just means the same thing. It's the cross of r and r. It's all real coordinates in the xy plane. As long as you can describe what the domain is, you should be good. Yeah. The range, on the other hand, is going to be typical. So, right, the domain, you're talking about what can go in. The range, you're talking about what you get out. So the range is all possible function values, which if it's a function of x and y, we usually think of the range as being all z values. So people would also write this as the function z equal to x squared plus y squared minus 4. And here's something that's going to be a common theme when you're talking about functions of two variables in general. You're not always, but certainly often going to see an x squared plus y squared show up. And it's going to be really important that you guys all get comfortable with knowing the fact that, oh yeah, I know that x squared plus y squared is always greater than or equal to 0, without a doubt. And then I'm trying to think about what values I can get out of this. So I know that if I subtract 4, I'm going to get what I want. So I subtract 4 from both sides. X squared plus y squared minus 4 is greater than or equal to 0 minus 4. Okay, well, I figured out what my range was. I figured out that my function is always greater than or equal to negative 4. And there's no upper bound, right? The possible values are negative 4 up to infinity. So my range here, written in the usual interval notation, is negative 4 with a bracket to infinity. You can go as low as negative 4 when x and y are both 0, and then you can get any number larger than that you want by picking the appropriate values for x and y. Level curves and traces help us graph the thing. So level curves, these are what you get by setting the function equal to a constant, and then seeing what the graph in that plane looks like. So I feel like maybe I should back up a tiny bit. We'll come to traces momentarily. So yeah, let me back up just one second. I'll make sure everyone's good with this. So I don't know if we talked about this or not. So we're doing a 3D graphing time in 17D as well, kind of. So it's weird. So easy to get mixed up what to talk about. So if I wanted to graph, say, the equation, yeah, we've definitely talked about planes. I'm insane. Sorry, we've totally talked about planes, right? You guys are all cool with graphing, hopefully, the plane like z equals 2, right? That would be the time that you say it. Cool. Okay, that's what I thought, but I felt like I had to check in just to be sure. So right, we can totally graph the plane z equals 2. It's just right the plane length it's up to. So it goes like this, and right, it's just like this. Right, it's this plane that's sitting 2 above the xy plane, which my pictures are never going to look good. So, okay. So the idea with a level curve is you're asking in that plane, z equal to 2, or z equal to 1, or z equal to 0, or z equal to 5, or z equal to pick a number, what does the curve look like? Meaning, what does the intersection of your surface and the plane look like? So for example, totally different example, if you knew that your, I want to do a different example. Let me think for 1 second here. No, it's going to be similar. Oh, that's fine. So if I knew that my equation was a sphere, maybe it's the sphere x squared plus y squared plus z squared equal to 9. It's a sphere centered at the origin with a radius of 3. Right, okay, my picture's garbage. But the idea is that if you take this sphere and you ask, okay, well, what if we ask, what do you get when you cut it or when you intersect it with the plane, let's say z equal to 2, So I go up 2 and go across here, back and forth this way. Well, I think everyone can hopefully visualize that when you take a sphere and cut it with like essentially, if you took an orange and you sliced it somewhere, not like, so just go get an orange and slice it really. If you take an orange and you slice off the top, what's the shape you're left with? It's a circle. So when you intersect the plane with the sphere, you get a circle. And you can totally see that. If you set z equal to 2, you get x squared plus y squared plus 4 equal to 9. You get x squared plus y squared equal to 5. You get a circle centered at x equals 0 and y equals 0. I don't care what z is, with a radius of the square root of 5. So that's the idea of a level curve. You're typically setting the function, which is usually z, equal to a constant, and then seeing in that plane, what do my curves look like? So let's go back to the function we're actually looking at, which is going to have similar level curves because of what it looks like. Although it's not a sphere, it's all right. So to find level curves, we're going to set the function equal to a constant. Now, usually the easiest way to do this is actually just to set it equal to a constant and then kind of isolate kind of a convenient choice, which I know it doesn't sound nice, but here's the thing. So let's say we're going to set z, or your function, equal to a constant. So now I've got x squared plus y squared minus 4 equal to a constant. And now I know that x squared plus y squared equal to a number squared is a circle with center of the origin. Or I should say center of 0, 0. So here's what I've got. I've got x squared plus y squared equal to 4 plus c. So this is going to be a circle. The center is 0, 0. And the radius is, well, it's the square root of whatever this number is over here. So the radius is the square root of 4 plus c. Let's see what that looks like. So the way we draw level curves is we draw them like we're drawing in the xy plane. And we are doing, what is it? X squared plus y squared equals 4 plus c. And I usually like to think about, this is why it's good to do the range before you do the level curves. What's the smallest thing c can be? Well, c is what the function is. So the small c value is the smallest value in the range. Smallest value in the range is -4. So c, and which seems obvious, I think. If c equals -4, it's kind of dumb. You have a radius that is 0. So when c is -4, you get a circle. It's just a point. That means different colors to kind of make it look hopefully nice. And then let's pick some convenient values, meaning let's pick c equal to -3. Well, then we're going to get a radius of 4 minus 3 is 1, square root of 1 is 1. And let me draw some marks here to try and make this look nice. Okay, so when c equals -3, we get a circle of radius 1. So I should not be drawing this dashed. And so typically with your level curves, you label them on the graph. So this is where c equals -3, which I know is probably impossible to read. Now I'm going to pick more nice values. So I would like my radius to be a nice number. So if I pick c equal to 0, I'm going to get x squared plus y squared equal to 4. So my radius is going to be 2. So here is c equal to 0. And let's do one more. let's do c equal to, so the next number, so c equal to 5 is going to be my next radius. So c equal to 5 gives me a radius of 3. So here's what this is. So this is like the topographical map, right? Where the different curves tell you if you're higher or lower, right? So here we're at the lowest, and then as we go up, and so we're starting low with the point, and as we go up, our circles are getting bigger and bigger and bigger and bigger and bigger. Now, if I was graphing this, I would also graph the traces. The traces are just what's happening in each plane. So in the, well, we already know what's happening in the XY plane, right? In the XY plane, you set z equal to 0. We already did that. We got a circle of radius 2. I'm not going to graph that because we already kind of have it right there in green. But if we look in the xz plane, so if we set y equal to 0, we end up getting, so I should write what our equation is again, right? Our equation is z equal to f of xy equal to x squared plus y squared minus 4. If I set y equal to 0, I'm just getting z equal to x squared minus 4, which is just a parabola that opens upwards, right? It looks like this. That's in the xz plane. And we're getting virtually the same graph in the yz plane. In the yz plane, if we set x equal to 0, we're going to get z equal to y squared minus 4, which is going to give us the same graph, just the yz plane. So now we try, now this is going to help us draw it three-dimensionally, I feel like. I think I can erase all these. So if we had to draw the three-dimensional surface, and I'd say, okay, now I'm going to go, let's just use black again. So I know, right? So 1, 2, 3, 4. So, right. So I know that, in fact, this is, I really like having the YZ plane graph because that one's the one that kind of looks like the kind of flat on the board plane. That's going to be my z equals y squared minus 4. So down here, I'm going to intersect with -2 and 2. And I'm going to draw a dash just for the moment to kind of give myself a chance to make everything look good. Let's see like not like that. Okay. And I know that I would also have a parabola not facing like this, but facing right like this, where it'd be like that. So you can't really see it so well. So, right. I would also have this kind of deal where it would come up kind of like this. And then our level curves would be circles. So like right in the, I'm going to try and draw in the same color. Hopefully this will work. So in the XY plane, when c equals 0, I'm getting this level curve. And then it would be plane z equals -3, right? I'm getting maybe, sorry, this is where my graph starts to fall apart. I'm getting that level curve. And when c is equal to 5, when z is equal to 5, I've got a radius of 3 and kind of like up here, pretend like this is it. So there is our paraboloid. right? It's a parabola, but then it's extended. And let me erase this piece up here because it's throwing me off. So hopefully that is kind of not terrible. But really, like, seeing what the traces in each of these planes look like helps me know, okay, I know it's gonna be like a parabola this way and a parabola that way. And then I know I get circles if I slice it as I go up. This is C equal to 5. Here's C equal to 0, or Z if you prefer. Here's C equal to -3. Right, so those are my circles. So this is basically, a lot of people like to think of this as the top-down view. Right? I'm looking at that from the top down like that. And I'm getting, I'm seeing all the circles at various things. And obviously you could make as many circles as you want, picking different values of C. But we usually like to try and pick values that make it so it's easy to like plot it. Questions about this? We're probably not going to do a ton of graphing of things, but it is good to have some sort of rudimentary idea of like what three-dimensional graphs look like, because it does become important to be able to visualize things at some point. Do a couple more examples. We'll talk more about domain and range. I should say, one of the reasons, when you're picking your values for C, they have, yes, the values of C are really the values of Z. And yes, they have to be in the range. Good question. One thing I will say is, one of the reasons we are talking about these three-dimensional surfaces is because when we start taking partial derivatives, what we're going to do is we're going to feel like, okay, if you're moving along the surface, but you're only moving in the x direction, that's the same as saying, I want to know what the rate of change of this function is if I'm moving in the x direction, which is the partial derivative of the function with respect to the variable x. So that's one reason, right? Just like when you look at a graph of a function in 2 dimensions, you're like the slope of the tangent line is like the derivative of that. The same kind of thing is to be true here. Where like if I wanted to find the derivative of this function in a certain direction, right? If I was like going in the x direction, I could be following this curve here and asking, okay, what's the derivative? What's the slope of the tangent line to this curve in the x direction at a particular point? So that's kind of some of the context is why we actually want to know what three-dimensional surfaces look like, because of the rate of change context that we're going to talk about. Also with directional derivatives, also with the gradient, three-dimensional surfaces are kind of important, they help us to understand what those things kind of mean. Let's look at another example. Let's look at something like this. What if I want to think about the function f of xy equal to the square root of y minus x squared? Okay, again, we're going to talk about domain, range, maybe some graphing stuff. Domain. Well, here I have a square root, so I know that the insides have to be greater than or equal to 0. Whenever I have like an inequality with multiple variables, I like to write it as an equality. So I'm going to think of it, instead of as y minus x squared greater than or equal to 0, I'm going to think of it as y minus x squared equal to 0, or y equal to x squared. So I'm going to graph that domain. So, and since I know so if it was strictly greater than or strictly less than, I would graph the boundary y equals x squared as a dashed line, so that it was not including it. But since it's greater than or equal to, I'm going to graph it as a solid line because I want to include it. So here's my y equals x squared. And now, the question you always have to ask yourself for an inequality is, which side of the boundary do you want to be on? Do you want to be up here, or do you want to be down here? And so what you do is you pick a point, any point that is not on the boundary. So pick a point, pick a point down here. Pick the point 0, -1. And then you ask yourself, does that point satisfy this inequality? And the answer is no, it doesn't. If you plug in 0 for x and 1 for -1 for y, you get -1 minus 0, which is -1, which is not greater than or equal to 0. So if you pick the side that doesn't solve the inequality, you say, oh, I want the other side. So I want all of this. Alternatively, we could have picked a point up here, like, I don't know, 1, 3, and plugged it in, and 1, if x is 1 and y is 3, 3 minus 1 is greater than or equal to 0. So if it does satisfy, then you're like, oh, that's the side I want. But you're always getting one side or the other side of the boundary. You're not getting both parts, unless there's something really screwed. Like, I guess you could have a fun, like, lots of things added together, but that would be kind of weird. Yeah, so how do we write the domain? Well, I mean, you could write it like this. If I had to write it kind of the most official way I could write it, I would probably write the domain as the set containing all x, y such that y is greater than or equal to x squared. That's probably how I write the domain. But if you said this, you'd probably be fine. You could also say everything above the parabola y equals x squared, above and including the parabola y equals x squared. I should point out that this domain is closed. A domain or a set in general is considered closed if it includes, I should say, there's a very technical definition about what it means to be closed. If you're a math major, you will certainly learn about it in some upper division math classes. But the more kind of easier to understand definition of being closed is that a closed set includes its boundary. So this set includes the boundary, so it's closed. It's also unbounded. Because, sorry, there were words I was going to say, because x can be, or so either x or y, or maybe both, can be as large as possible, right? There's some direction where y can increase or decrease without boundary. Same for x. Right here, right, x and y can both get super large, right? X could be a bajillion as long as y is a bajillion squared. So, right, they're unbounded. There isn't some I don't want to use the word close. There isn't some shape that our domain is stuck inside of. Okay. What else? We were maybe going to graph it. Yeah, let's graph it. Oh, we were maybe going to talk about the range first. So the range is not terrible here. The range, well, I've got a square root. It can definitely be as small as 0, right? If x and y are both 0 or both 1, or y is 4 and x is 2, right? There's lots of places on the boundary where the range is equal, the z value is equal to 0. And then we can get any positive number. So our range here is 0 to infinity. Level curves. I've already drawn one of them. That's the level curve when z or c equals 0, right? And it kind of depends on what you want to say. Sure. Kind of running out of room here, as usual. So for level curves, right, we're going to set c equal to the square root of y minus x squared. And then if I was trying to graph the level curves as easily as possible, I would isolate y, right? Because again, I'm graphing in the xy plane when I'm graphing the level curves. So I'm going to say, okay, well, square both sides, c squared equals y minus x squared, add x squared, so that y equals x squared plus c squared. So when c is 0, you're going to get this one here, right? You're going to get y equal to x squared. So I think I can graph this all right. Sure, let's try that. Try and make this look somewhat decent. Wow, totally missed all my points there. That's all right. So there's c equal to 0. And then we can also have, now be careful here. If I was not paying attention here, I might think c could be positive or negative. Because if c was negative, okay. Like if c was negative 1, y equals x squared plus 1, that's fine. But you have to remember, your c values, your level curve values have to be in the range. And the range is that. So if we pick c equal to 1, we get just the parabola shifted up 1. So c equals 1, we get, my pictures are not going to be good. Right, c equals 1. And then if we pick c equal to 2, we're up at y equals x squared plus 4. Right, so we're looking like that. Sorry. And my parabolas don't look great. So basically, oh, we can do something cool. Yeah, okay. So basically, right, if we go higher up, every value we're going to get is going to be, what's the word I'm looking for? Just a parabola kind of scooted further down the y-axis. I don't think the traces here are specifically useful because, I don't know, maybe. Let's look at, yeah, I might as well look at the traces. We already know the traces in the x, y plane. That's just setting z equal to 0. So there's your trace in the x, y plane. So what you maybe want to do is kind of think about if you took this and flattened it out, so something like this, where the x was coming out and the y was going to the right. You see, like this is the lowest one, and then as you move up, you're going to move right. It's going to be kind of like kind of like that. I know that doesn't really help, but you'll see in a minute. I hope. But if we did the traces, right? If we let y equals 0, we're going to get z equal to the square root of 0 minus x squared. That's kind of funky, but not really. No, it is kind of funky, right? You don't really get anything there, right? Because no matter what x is, z is going to be 0. I mean, sorry, no matter what x is, negative x squared is going to be negative, which means you only get something when x is 0 and z is 0. So this is not super helpful. You get kind of nothing. But when x is 0, you do get z equal to the square root of y. So that's a little helpful. So in the yz plane, you're going to get z equal to the square root of y, which is going to look like your usual square root function. Like that. All right, so let's see if we can make this work. So in the 3D kind of graph here, do that because it might get in the way here. I'm going to draw my square root function. Try and draw it somewhat precisely here. The problem with this one always gets in the way, kind of. Sure, let's say it's over here. Here's my square root function. Looks like that. And then my traces, right? So my traces in the x, y plane, so it's going to look like the parabola coming out this way. So there's one. And right, also back here like that. And then as I go higher up, right to this point here, I'm also going to get like a parabola looking thing. I don't think my picture looks wonderful. It looks, and then it makes me go one higher, right? You go up to here. Right, every level curve is a parabola. I think Grant's picture is much nicer. Let me share with you a couple things. So first, here's the picture Grant has drawn for the same one. I think that does a little bit better job of getting at what the shape looks like. But actually, let me show you. You can actually, so in Desmos, some people have come up with some 3D, some ways of making 3D pictures. So if I want to, and I'll share this link with you guys if you want it. If I want to graph the square root of y minus x squared, oh yeah, there it is. Now I want to move it around. Oh, I can't. Oh. I have to use these little slider things to turn it around. So I'm trying to get it. The problem is sometimes the orientation, like it kind of like flips the way you see things. So you can kind of feel like things are going backwards very quickly. Ooh, what I should do is I should reset this. So this, if you, yeah, this is the function that starts off as, and then we can delete all that. There's the usual orientation. So it starts off with the x-axis pointing that way, the y-axis pointing that way, and the z-axis pointing that way. But then you can rotate around the z-axis. You can rotate around the, I mean, I guess it's kind of, shouldn't really say it that way. It's more, yeah, anyway, you can play around with it is what I should say. You can go that way, you can go that way, you can go that way. It's neat. It kind of helps. It can kind of help you see things. Maybe, I don't know. It can get kind of weird. So, ooh, fun times. Anyway, you can also do other things. Let me turn the orientation back around. The problem is, like, I always get off and I'm like, okay, which way am I going here? Oh, that's kind of neat. It's always hard to get going straight. There we go. That looks about like how we started off. Kind of. Except. Anyway, you can also play around with some of these slider things down here that can do real funky looking things. This one's not the one I meant, or you can increase that. These are the ones you can kind of make your picture go bigger. You can make it be less fine, more fine. Anyway, I think that's enough of that. So yeah, here's the link to that if you want it. It's useful somewhat to kind of help see things. But you can see, right, our graph definitely looks like that. And yeah. So where was I? I was talking about that. That's a good example. Let's look at a few more examples. Yeah, sure. Let's look at say this one. Let's look at f of xy equal to 1 over the square root of x squared plus y squared minus 4. Okay, let's do the whole shebang. Domain, range, level curves, maybe some traces. I don't know. The traces may or may not be super helpful. So domain. So here we have some stuff inside the square root. So we know that x squared plus y squared minus 4 has to be greater than or equal to 0, except we don't actually want it to equal to 0 because it's also in the denominator. So we really just want x squared plus y squared minus 4 to be greater than 0. If you're seeing an x squared plus y squared, that's kind of a thing you want to isolate. So I'm going to rethink of this as x squared plus y squared greater than 4. And we know that x squared plus y squared equal to 4 is a circle of radius 2. So here our domain, the boundary of our domain is a circle of radius 2. And notice I'm drawing it dashed because I know I don't want to include the boundary because x squared plus y squared has to be greater than 4. And the boundary is where x squared plus y squared is equal to 4. And I know I don't want it to be greater than equal, I just want it to be equal. So now I have to decide which side of the boundary do I want. I usually like to pick a point that I know isn't in it to show you, right? If I pick 0, 0, 0 squared plus 0 squared is not greater than 4. So 0, 0 isn't in the boundary, so I want everything outside of the circle, which I'm not drawing very well. So my domain is all of that. All points outside circle of radius 2, center at the origin. You can also, so the nice thing about writing the domain in the set notation is to literally just write the set containing x, y with the inequality. So right, you can also write this as the domain is the set containing x comma y such that x squared plus y squared is greater than 4. However, I will say writing this way doesn't indicate in any way, shape, or form that you know what the region looks like. So it is good to actually be able to think about what the region looks like. Let's see. This domain is open and unbounded. Open because it does not include its boundary. Unbounded because x and or y can be super large or super negatively large. The definition of open to me is a little bit easier to understand, like the formal definition. Not including your boundaries, the easy way to say it. But the more precise way of saying that a set is open is if any point in your set, there is a small circle around that point that is also in your set. Fully contained in the set. So like if I pick a point like right here, I can draw a super small circle around it that is also fully contained in my open set. Right? No matter how close to the border I get, I can always draw a tiny little circle around that point that's still contained in this outer part. But if the set included its boundary and I try to draw a point on the boundary, if I draw a point on the boundary and I draw a circle around it, I'm going to get some stuff in here and in here, which is not fully contained in here. So that's the more precise definition of what it means to be open, is that any point in your set, there is a circle around it that is also fully contained in your set. Ooh, that's a lot of cracking. Okay, just like crack everything now. What about the range? Ooh, the range. Interesting. So this one definitely takes a little more work to think about what the range can be. Here's where I usually like to start with the range. I like to start with the domain. So here's what I mean. We're looking at the function 1 over the square root of x squared plus y squared minus 4 minus 4. And we are saying that x squared plus y squared has to be greater than 4. In this case, you probably don't have to start with it, but it's kind of nice. I'm going to work backwards to get to here. So I'm going to subtract 4 from both sides. And it has to be greater than 0. And then the square root of it, the square root of a thing that's bigger than 0 is still bigger than 0. So now here's the thing. I want this to be bigger than 0, which means it's also less than, right? There's no upper bound on it at the moment. So then I'm going to take the reciprocal of both sides and say, well, 1 over infinity is 0. It's less than 1 over this. It's less than 1 over 0. This one wasn't super interesting. The range is 0 to infinity. Okay, not super exciting. But it does kind of help us graph it. So we know that, yeah, helping us graph it. Graph's going to be interesting. Sorry, get a little bit crazy here. So, gotta do level curves. Level curves, okay. Level curves. So C can be anything that's positive. So set this equal to C and then solve for, yeah, okay. So I'm going to flip both sides, say that the square root of x squared plus y squared minus 4 is equal to 1 over C. Square both sides. Equals 1 over C squared, and add 4 to both sides. So x squared plus y squared equals 4 plus 1 over C squared. Again, our level curves are going to be circles where the radius is the square root of 4 plus 1 over C squared. Okay. So let's think about this for just a second. If C is very large, 1 over C squared is very small, and 4 plus that number is very close to 4. So as C gets very, 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 very large, the radius gets closer and closer and closer to 2. So let's pick a kind of big number. Let's pick, I don't know, let's pick 10. Right? If C is 10, I'm sorry, I'm trying to draw the level curves, not the whole thing. If C is 10, the radius is going to be 4 plus, sorry, the square root of 4 plus 1 over 100, which is so close to 2. It's a tiny bit bigger than 2. So 1, 2, right? So here's the radius when c equals 10. And then as c gets smaller, the radius is going to get much, much larger. Right? So, I'm going to erase some of this here. Now let's say if c is equal to 1. Sorry, this is getting a little bit. 1, 2, 3, 4. So if c is equal to 1, 4 plus 1 is 5, square root of 5 is, I don't know, 2 point something. So right, so here, there's c equal to 1. C can't ever be 0, but c can get really, really big, right? Like if c was, I don't know, 1/2, 1 over 1/2 squared would be 1 over 1/4, which would be 4. 4 plus 4 is 8, squared root of 8 is almost 3. So, right, we can get to 3 when c is almost 1/2. I don't know. I guess I could, right, if I want that to be 3, 9 equals 4 plus 1 over c squared. C is like 1 over the square root of 5. I don't know, it's weird. But you can kind of see, right, that as c gets smaller and smaller and smaller, our circles are going to go way, way out. So at the highest, the radius is 2, right? And c can get super duper high. At the lowest, down to 0, c can get very, very large. So here's what our graph kind of looks like. This is where actually a trace would be very useful. So if I do a trace in the yz plane, if I let x equal to 0, my trace is z equal to 1 over the square root of y squared minus 4. So I just graphed that for a second. Let's see. Sorry, my brain is getting a little bit bonkers here. Yeah. So y has to be bigger than or equal to 2, right? If y was 2, we'd have division by 0. But then after that, like if y is 3, we're going to get, the bigger y gets, the smaller z gets. So right at 2, we're getting very, very large values. And then we're going to kind of like, when y is 3, we get 1 over the square root of 5. So we're getting something kind of like this. And the same thing on the other side. And then it's kind of, whoops, I drew it at -1. Sorry. -2. So we kind of have a cylindrical vertical asymptote. And then we've got kind of our like that. So it's, yeah, it's kind of, when you've got level curves that get to be bigger and bigger circles as you go closer and closer to the xy plane. It's kind of cool. Let's do one more without graphing it. And then we will, I don't know, and then maybe we'll talk about limits for 20 minutes. Let's see. Let's say we wanted to find, I know I had some examples that were, sure. Let's look at, I just want to find the domain and range of, what have I got here? Let's do 2 and then we'll move on. Let's do f of xy equal to, sure, the square root of 16 minus x squared minus y squared. And then we'll also do, after that, g of x, y equal to, what do I want? Sure. Log base 2 of 32 No, that's not what I want. X squared plus y squared minus, no, plus 32. Sure, that seems fine. Okay, so here first, domain. Stuff has got to be bigger than or equal to 0. I want x squared plus y. So a lot of these are going to have x squared plus y squared. So I'm going to have 16 is greater than or equal to x squared plus y squared, which means I have x squared plus y squared less than or equal to 16. That's going to be circle of radius 4, including the boundary. And do I want the insides or the outsides? I want the insides because 0, 0 satisfies the inequality. So my domain is, if you like, you can write it as the set containing xy such that x squared plus y squared less than or equal to 16. Closed, bounded. And it's bounded because x and y can only be so large, right? There's no never-ending, I shouldn't say that, there's definitely never-ending possibilities, right? There's literally an infinite number of points in here, but x and y, x can only be so big, right? X can only be as big as 4. Y can only be as big as 4. Only as small as -4. Same for x. The range, on the other hand, so this is the type of problem where the range actually, you kind of want to, I like to work with what I've got. So here's what I know I need. I'll come back to this one. For the range, I'm going to say that I know 2 things. I know that I definitely have the domain x squared plus y squared is less than or equal to 16. But there's something else I have to be aware of. I have to be aware of that x squared plus y squared is greater than or equal to 0. You can do this kind of however you want. Like, you could totally look at this as the square root of 16 minus x squared plus y squared and just say, okay, I know the smallest x squared plus y squared gets to 0. And then the biggest that's allowed to be here is 16. So if this goes from 0 to 16, the insides go from 16 to 0. So you get 0 to 4. But I like to work it this way. So I know I have this. It's got to be less than or equal to 16 because of the domain. It's got to be greater than or equal to 0 because it's x squared plus y squared. And then we're going to try and make this look like your function. So first, negate everything. When you do the negative of everything, you change the order of the inequality. So you get 0 bigger than or equal to negative x squared plus y squared bigger than or equal to negative 16. Then add 16 to each part of the inequality. So 16 minus 0 bigger than or equal to 16 minus x squared minus y squared bigger than or equal to 16 minus 16. Then take the square root of everything. Square root of 16 bigger than or equal to the square root of 16 minus x squared minus y squared bigger than or equal to the square root of 0. So, oh, look, my function is bigger than or equal to 0 is less than or equal to 4. So the range is 0 to 4. That's the idea I'm employing here. This would be the top half of the sphere of radius 4. Let's look at the other one. So let's see here. Log base 2, x squared plus y squared 32. So not y, z or f of xy. Log base 2, x squared plus y squared plus 32. So domain. We need x squared plus, I feel like I picked this to be not exactly what I want it to be. No, that's fine. X squared plus y squared 32 greater than 0. No issues, right? This is going to be everything. Yeah. Okay. So it's going to be R2. That's the way I would say it, R2. Range Well, here's what we know. I know that x squared plus y squared is definitely greater than or equal to 0, right? Always. Then I'm going to make this look like that. So x squared plus y squared plus 32 is greater than or equal to 32. And then take the log base 2 of both sides. So here I'm getting that my function log base 2 of x squared plus y squared plus 32 is greater than or equal to log base 2 of 32, which is 5. So my range here is 5 to infinity. Okay, one more thing. The domain is definitely unbounded, right? It's literally everything. Let me ask you guys, is it open or closed? Well, it's definitely open, right? The actual answer is it's both open and closed. So typically, whatever space you're working in, the set of everything in that space is an open set and a closed set. So R2 is open and closed. I think the kind of the easy way we kind of say this clearly. So the way I talked about openness, I think it's pretty obvious, right? Any point in R2, you can draw a circle around it. It's still an R2. The boundary idea is a little less intuitive, but here's the idea. Closed sets include their boundaries. There is no boundary. So the set definitely includes the nothing boundary that isn't there. So the set R2 does include its non-existent boundary. So it's also closed. There's a deeper explanation to that, but that's kind of the short version of the why you can also say it's closed. But yeah, so the sets like the number line R is also a set that is open and closed. Clearly open, also kind of weirdly closed. Yeah. Times 245. Okay. Let's talk about limits a tiny bit, because that's definitely something that's going on as well. Where'd you go, limits? So limits. So what's going to be going on here is we're going to be asking, instead of like what's happening to a function of x as x approaches something, we're going to be asking what's happening to a function of x and y as you're approaching a point in the xy plane. So let's look at some easy examples. What's the limit as xy approaches the point 2, 3 of x squared plus y squared minus 1? Well, that's pretty straightforward, right? There's no weird undefined, right? So most limits we saw like in 21A, usually you're getting some 0 over 0 garbage and you had to do some factoring and canceling, whatever. Here, that's not the case, right? You can say, oh, x is approaching 2, y is approaching 3. We're getting 2 squared plus 3 squared minus 1, which is 12. So just like in 21A, if you can plug in the values and it's defined, that's typically your limit. But a lot of the time, most of the time, we're not going to do that. So what if instead we have something like, I don't know, the limit as xy approaches 3, 3 of the following: x squared minus y squared over, that seems boring to me, but fine, x minus y. So looking at this is definitely a 0 over 0 indeterminate form. If you plug in 3 for x and 3 for y, you get 0 on top and 0 on the bottom. And in this case, we can factor, right? This is going to be equal to the limit as x approaches, as xy approaches 3, 3 of x minus y times x plus y over x minus y. And then we can cancel the x minus y's. So we end up getting the limit as xy goes to 3, 3 of x plus y, and then you just plug it in, you get 6. But then, let me make sure I looked at this before. Yeah. So sometimes, not a lot, but sometimes these limits, you will get something factoring and canceling to get rid of your 0 over 0 problem. Much like in 21. Sometimes you don't, like the following example. So I will say a lot of the time, not all the time, but a lot of the time, if you have a limit where x, y is approaching 0, 0, often it's going to be a does not exist answer. So here's the limit. Limit is x comma y approaches 0, 0 of 4xy over x squared plus y squared. And actually, I'm going to come back to this because I want to point out how we're dealing with this. So let me think of a good example here. Sure. Let's say I wanted to find the limit as x approaches, I don't know. What do I got? X approaches 2 of x squared minus 5x plus 6 over the absolute value of x minus 2. And so if you think about this graphically, the idea is that whatever the graph of this looks like, you're asking what's happening as we approach 2 from the right and as we approach 2 from the left. And for the limit to exist, any direction we approach 2 from, the limit has to be the same. Well, absolute values are always a problem. So we have 2 different options, right? If we do the limit as x approaches 2 from the right, okay, if x approaches 2 from the right, that means x minus 2 is positive, which means the absolute value of x minus 2 is just x minus 2. And the numerator does factor as x minus 3 times x minus 2. Those x minus 2's cancel. So you get 2 minus 3, which is negative 1. So if we approach 2 from the right, the limit's going to be negative 1. And yeah, it looks like this. So we're approaching 2 from the right, we get negative 1. But if we approach 2 from the left, here's the problem. From the left, top still factors x minus 3, x minus 2. But the bottom, now that we're left of 2 or less than 2, x minus 2 is negative. And to make a negative thing positive, you take the negative of it. Right? If x is like 1, 1 minus 2 is negative 1, and the absolute value of negative 1 is negative 1, which is 1. So then the x minus 2's cancel, and you get x minus 3 over negative 1. It's 2 minus 3 over negative 1, which is negative 1 over negative 1, which is 1. So as we approach 2 from the left, the limit is equal to positive 1. This is what the graph of this looks like, by the way. And you can totally see that as you're approaching 2 from either side, the left and the right-hand side don't meet up. So the limit does not exist. So here's the takeaway from this. If you approach 2, or whatever you're approaching, from different directions and you get different answers, the limit does not exist. Well, in one dimension, right, when you're talking about just what x is doing, there's only 2 different ways to approach what x is equal to, from the right and from the left. But if you're talking about being in the xy plane and asking what xy is approaching, 0, 0, there are literally an infinite number of ways to approach 0, 0. So if we're approaching, right, I'm not going to graph this, although I will show you, right, on my 3D graph in a second. If I'm trying to approach the point 0, 0, I can come at it this way, I can come at it this way, I can come at it that way, right? There's literally a million ways in the xy plane, right? If I'm actually in the xy plane, there's, right, I can come at this from so many different directions. So usually, if we have a guess that the limit doesn't exist, which is usually our guess until we think it does. So if you're approaching 0, 0, you're typically going to start from the point of view of, I think this limit probably doesn't exist, because it usually doesn't. And then you're going to pick different paths. Different paths that go through this point, 0, 0. So a typical choice is picking something like y equal to x. So y equal to x definitely goes through the point 0, 0. So I'm going to put, so I'm going to set all my y's equal to x's. So this is going to make this limit become the limit as just x approaches 0, right? Because if x is 0, if x is approaching 0 and y is equal to x, then y is also approaching 0. And I'm going to have 4 times x over x squared plus x squared. We'll check this out. This simplifies. This is going to be the limit as x goes to 0 of 4x squared over 2x squared. I can cancel the x squareds, and the limit as x goes to 0 of 4 over 2, the constant 2 is just 2. So coming at it from, I know it's kind of hard to draw, but if I was coming at it from like that direction, right, straight at it from the, right on the y equals x line, the limit ends up being 2. So I'm coming at it this way, and it's going to go up to 2, and I'm going right there, 2. Maybe like that. So from that direction, the limit's 2. But if I come out from the direction of, I don't know, let's say I come out from the direction of y equals 0. Right, so here's y equals 0. It's just the line, the x-axis. So if I come out from the y equals 0 direction, I get the limit as x comma y. Sorry, I'm plugging in 0 for y. So I'm just going to have the limit as x goes to 0 of 4 times x times 0 over x squared plus 0 squared. Well, 4 times x times 0 is 0. So this is the limit as x approaches 0 of 0 over x squared. But x isn't 0. It's approaching, but not equal to 0. Meaning this is 0 divided by a non-zero number, which is 0. So this is the limit as x goes to 0 of 0, which is, hey, 0. So what that means is I come at it from this way, the limit's 0. So from this direction, I'm getting 2. From this direction, I'm getting 0. They're not the same. The limit doesn't exist. And one thing I want to stress here is that people often forget about using the path y equals 0 or x equals 0. But they are valid paths, and they usually almost always make it work out pretty easily. So graphically, if you look at the graph of this thing, it looks very bizarre at the point 0, 0. Let's see if we can graph it. Let me reload this. So here's what it looks like if you care. Okay, come on. Oh, I didn't mean to do that. Okay. So, right, we've got 4xy over x squared plus y squared. And you can hopefully kind of see, let's swirl it around here. No, not that way. Let's go this way. Right, you can see that at the origin, bonkers stuff is happening, right? From one direction, like, right, it's just doing all kinds of, it's messed up. We've got a very discontinuous anomaly there. So yeah, at the origin, it's getting very large and very twisty and hard to really know what's happening, but hopefully that maybe kind of helps a tiny bit.